Hello and welcome to another video from HPart. Today we will be exploring the design of prism-based spectrometers. And we will be using Fresnel, which is a free optical design program available at h-part.com. We're going to start our video today by taking a look at one of the designs we did in the last video. This was a point source collection lens, and it carried out a relatively simple task. It started with light from a point source over here, and it collimated it between these two lenses. And then it focused that light onto a detector over here. Now, I mentioned in that video that these lenses are very useful for spectroscopy, because if you care about light at a particular point and you want to collect that light and launch it into a fiber for spectrographic analysis, this is just the optical design for you. However, at this point you might be wondering, what does this have to do with designing a prism-based spectrometer? Well, it turns out that this design includes almost everything you need to make a spectrometer. All we're missing is a single element. And to see why that is the case, consider the following. Suppose we add an element right here between these two lenses. And what this element does is that it shifts the light, kind of bends it, deflects it, based on the wavelength. So let's just suppose that it lets the red light through more or less straight, and then the blue light, it kind of bends. And it does that across the y-axis. So it's consistent radially around the lens. Now what's going to happen is the lens, this lens over here on the right side, it's going to see collimated red light heading without modification. And it's going to do just what the system is doing right now. It's going to focus it to this point. But it's also going to see collimated blue light heading at this angle right here. And it's going to take this collimated blue light, which is all collimated relative to itself because our element deflected everything the same if it was blue. It's going to take all this collimated blue light and it's going to focus it to a different spot. Oops, let's get the color right. Maybe down here. And that's all a spectrometer is. It's just a point source collection lens with an element sandwiched in between that bends different wavelengths of light differently. We're going to design exactly this system using these two lenses and using a prism as the element. But a Scherszny-Turner spectrometer follows exactly the same principle. Instead of lenses, it uses mirrors to collimate and then focus the light. And instead of a prism, it uses a grating in between them. And that's all a Scherszny-Turner spectrometer is. Just a point source collection optic with an element in the middle that bends the light differently based on the wavelength. So now that you have this basic motivation, let's jump into the actual design. All right, here we are in a nice new design. So let's get started. First thing we need to do is create an emitter. So we'll just work our way from left to right through the design. Create this point source emitter. I'm actually going to put it at minus 25 for this, just because I want to create a little space between the emitter and the origin. And then I'm going to create an aperture. Now we haven't worked with apertures very much, but they effectively act to block the light, and we're going to use it here to neck down the light so the light that enters the prism and thus our spectrometer is roughly speaking paraxial. If we didn't have an aperture, we get a lot of light near the edges of our lenses, and the aberrations would ruin the performance of our spectrometer. So let's go ahead and create a basic aperture here. And we're going to put this at about 15. All right, so now we've got our aperture in place. And the light's going to travel out of our emitter and it's mostly going to get blocked, and a small cone is going to travel through the aperture. So to see that, let's go ahead and add a bunch of emissions. So the first one is going to be the rainbow emission. This will be everything from violet down at 400 up to red at 700. Then let's also go ahead and add the violet emission, if I could spell. And we'll put that at 400. And then we'll also add the red emission. Red. And we'll put that at 700. Okay. Now let's go ahead and cast these. All right. Well, it's not terribly exciting, but you can see the cone of rays traveling towards the aperture. Now this will go a little farther if we add a lens behind it. Now just with the point source lens that we talked about, the lens element that we're going to add here is going to take this cone of light that is exiting our emitter, and it's going to collimate it. So let's go ahead and add that lens. Now it's worth noting NBK7 will be fine because we're just in the visible. We're going to start with the PCX lens. We're going to have the basic parameters, and we're going to put it out at 25 with no rotation. All right, so there we go. Now let's go ahead and cast all the, well, we'll just cast the violet. Okay, perfect. So now we can see that we've got light moving through our aperture over here, and then traveling through the lens over here. And it's already roughly collimated. It's not perfect, but it's good enough for our initial layout. Now before we proceed, we're going to be using a couple of things we haven't used so far in this video series. So I want to motivate them and kind of get you ready. The first one is an extrusion. Now the extrusion is pretty obvious. That's how we're going to make the prism. An extrusion is just taking a 2D profile and pushing it out of the plane to make a 3D shape. It's kind of like how a pasta maker makes pasta. The other thing we're going to use are local coordinate systems. Local coordinate systems allow you to group a bunch of elements together in their own coordinate system and then reference that to another coordinate system. And we're going to make heavy use of that here. To see why, let me explain roughly what the layout is going to look like. So I'm going to enable my rather poor drawing skills once more. So we've got light that is traveling this away, and we're going to have it hit a prism that's going to look something like this. And it's going to travel through the prism, and it's going to bend ever so slightly when it hits each surface. Then it's going to hit a lens, which will focus the collimated light, and then somewhere down here, and we want to make the detector somewhat far away to amplify the spread of the light we get from the prism, we're going to put our detector. And the light will then travel through the lens, and it will focus down here at the detector. Now thinking in terms of coordinate axes, this pair of elements, the second lens element and the detector, these guys are all on one coordinate axis. And it should rotate as the prism is rotated. The prism itself is actually a separate coordinate axis. And we're going to rotate it slightly so that we can get the light oriented correctly. So we have two coordinate axes. We have a prism coordinate axis up here, which we will use for our initial rotation, and we have the back end train of the lens and the detector that will be on a second coordinate axis that's going to reference the prism coordinate axis so that it rotates as the prism rotates. All right, so my poor drawing aside, let's implement it. So first thing we need to do is create the coordinate system for our prism. And we're going to rotate this ever so slightly. 18's a good initial guess. We're going to call this the prism coordinate system. And as you notice, it's right out here where we wanted our prism to be and where we wanted it to be tilted. Now, the reason we didn't just make the prism in the world coordinate system and just tilt it there is that if we rotated the prism, it would not rotate the coordinate system, and thus we couldn't have the other lens elements rotate along with it. So we're making this prism as kind of the base so we can communicate that rotation through to another coordinate system. So now that we've added this prism coordinate system, let's put the prism on it. So this is going to be an equilateral triangle. We're going to set it with 25, 25 side lengths and a width, which is the thickness, of 25 as well. And we're also going, well, we'll just go ahead and create it and see what it looks like. Okay, so it appears to be in the wrong place, and it's, now we got to get in the right place. So let's start here. First thing is, we notice the coordinate system that it's in. It's in world coordinates. That's not what we want. We want prism coordinates. Okay, that's looking a lot better. But it's not oriented correctly. So we need to rotate it. Specifically, we need to rotate it about the green axis, the y-axis, by about 90 degrees. So let's see how that looks. Ah, that is now looking a lot nicer. We could make this less wide, but for now, it's going to be fine. Okay, great. So we've created our prism, and we've installed it, and we've also now rotated it. So let's go ahead and recast the violet emission. And now we can see a rather beautiful set of rays as the violet transverses through the prism. A lot of the rays get refracted back. A lot of them make it through and then travel out. Now let's also just go ahead and cast the red. Now I don't know if you saw it, it was a little subtle, but I'll open up the display so you can see it again. Turn on the emission filter, uncheck rainbow. I'm going to uncheck red. Sorry, I'm going to check. Okay, there we go. Up, we need to cast violet again. Let's go ahead and cast violet. And let's cast red. Oops, we actually have to cast them all. There we go. Okay. So now we're looking better. So now as you see, it may be hard to see, but I'm gonna zoom in on this. As I uncheck the violet, you can see how the rays shift slightly. And that's what a prism does. Because of the variable index of refraction by wavelength due to NBK7, i.e. the dispersion of the material, which we can just see right here, NBK7, the dispersion at 700 is about 1.513, whereas the dispersion at 400 is about 1.52. And that means the angle at which the light bends through this is going to be different. And so the red light is going to get bent a little bit less and a little bit less here. And the blue light is going to get bent a little bit more here and then a little bit more here again. And you can see that in that the blue light is shifted lower than the red light. So this is the effect of the prism. Now, just a side note, prisms are not the most effective way to accomplish this kind of wavelength bending. Diffraction gratings work a lot better. But prisms are simple, straightforward, and follow our prism-based, lens-based design theme. So we're going to go with it. So now I'm going to go ahead and disable the emissions filter, and we can see all of our emissions being cast, which I think is rather pretty. And now the next thing we need to do is create the coordinate system that's going to hold the other lens and the detector. So I'm going to call this the focusing coordinate system because the lens focuses. So focusing, and I'm going to put that on the prism coordinates. It's going to be at the origin of the prism coordinate system, which is right here, rather than the origin of the world coordinate system. And it's going to be rotated about the x-axis, which is going into the plane. It's this red axis going down here. It's going to be rotated about that about, well, for now, we're going to call it 25 degrees. It's going to be pointing down here. So let's go ahead and create that. Okay. So now we've created our coordinate system. We can see it. It's right here. And this is the z-axis, which is pointing down our new optical axis. That might be a little severe, but that's okay for now. And now let's go ahead and create our focusing lens element. So this will be a PCX lens. We're going to rotate it 180 degrees. It's going to have a z position of 25. And we're going to put it on the focusing coordinate system. Because we put it on the focusing coordinate system, we don't have to calculate x and y in world coordinates, which would be complex and a pain. We just have to let the software do it for us. And go ahead and create it. So there we go. So now we have our focusing optic. And if we go ahead and say run the violet emission, we can see that it's now traveling through the focusing optic and will eventually go focus on the detector, which we will create now. As I mentioned, we want to create this detector pretty far away so that we give the slight angular differences the prism creates enough time to be turned into reasonably large position differences on the surface of the detector. And in real life, this detector would probably be a line scan camera or a regular camera. So we want to space it out so we can improve our resolution. So I'm going to go ahead, we're going to make this detector a little bit taller, just so it's easier to catch these things. And of course, we'll rotate 180 degrees, so it's looking up the optical axis. And as far as the coordinate system, we want to put it on focusing. So now we have our detector way out over there, ready to catch the light. And of course, we'll put a detection there. We don't need any gates. We just want to see where it lands. I'm going to run violet again. And you can see we're actually starting to focus the light onto the detector, which is wonderful. And I also think this looks reasonably pretty. So the next step would be to actually start to optimize. I'm actually going to cast all of these, and you can see the big difference by wavelength that's starting to already form here. But we really want these two to actually focus to points on the detector. So to make this a little bit more clear, I'm going to hide the rainbow emission and talk about what we currently have. You can see that the red light is already starting to split from the violet light. And we really want these to be focused at points here so that they would image, so that we would image a single point of our source. We want to image this source onto this detector, and we want the red image to be up here, and we want the violet image of our source to be down here. So we've got some optimization to do. Now, the next step that we want to do before we start thinking about how we're going to optimize things is we want to do a couple of basic setup things to make the optimization go better. The first is we want to create a light path. So the light path is going to allow us to get rid of all this stray light. It'll make the optimization algorithms run faster, and it'll make it clearer as to what is going on. So I'm going to go ahead and work through this light path, and hopefully I get it right. So we're going to start with the aperture itself. Then we're going to move on to the refraction, to the first lens. Then we're going to move on to our prism. Then we're going to move on to our second lens. Oh-doop-a-doop-doo. And finally, the detector. So now, just to make this easier to see, we start at the aperture, went through the first lens, left, right, through the prism, 2 and 3, then through the second lens, which is rotated 180 degrees, we went right, left, and finally we hit the detector. So now that we've created the light path, we're going to add it to all these emissions. Doop, doop, doo. Doop, doop, doo. Okay, great. Now we've added the light path. Now, moment of truth, we're going to cast all of these and make sure that they are on the light path. Beautiful. All right, great. So now we are seeing all the light that's on the light path. It's much clearer because we're now rendering only rays that are not stray, so we're getting a lot more rays down here, and we can really see the split. And I'm going to continue to keep violet hidden, just so this looks prettier. We're actually not going to use the rainbow emission for any optimization. We're just going to try to get red and violet to focus to a point with high collection efficiency. There is one more thing that we should consider before we start optimizing, and that is that if you look carefully, you'll notice that the light is actually not coming into the center of this focusing lens. So we want to actually shift it in its green y-axis up a little bit, and we want to shift the detector up correspondingly so that the light is centered on our lens. The reason for this is that lenses, well, one, it's good to be centered in terms of the different wavelengths, but also lenses behave better when you use them more centrally, right? By being uncentered, we have more light going up in this marginal area, which is going to suffer from greater aberrations, especially at the distance. So we're going to add a formula. This formula is going to be called y-shift. And it's just going to have a single free variable, which is going to be y-shift. And for now, we're just going to call it 5. And all the formula output is y-shift. That's it. Just essentially a constant. And then we're going to use that to shift. Hopefully I got the sign right. There you go. We're going to use that to shift our lens so that it's roughly centered. I think that's a little bit big, actually. I'm going to tune that down to maybe 2.5. Ah, that looks a lot better. And we're also going to use it to shift the detector for symmetry's sake. Okay, great. So now we are coming more or less with the correct shifts. And now the next thing is to start to set up the analyses that we're going to optimize with our merit function. So as I mentioned, we care about collection efficiency. We want to get light onto our detector, and we care about spot size. We want to have a precise ability to image each different wavelength. So we're going to create a collection efficiency analysis for the violet emission. We only care about filtering stray rays. This doesn't matter because we have no gates, so we'll just leave it as is. And we're going to create another collection efficiency analysis. Actually, I'm going to label the first one. I'm going to call it CE violet, just so it's clear. Then we're going to create a CE red off of red. We're going to filter stray rays. Then I'm going to create another analysis called spot size, and that's going to be, I'm going to call that SS violet. I'm going to use violet, filter the stray rays. Then another one, SS red. That's going to be red. And again, we're going to filter the stray rays. All right, so we've created our analyses. Let's just take a look at how we're doing on violet. As you can see, we're not getting a lot of light over to our detector. But we are getting a reasonable percentage of the amount of light that we are actually getting into the cone, which is going to be roughly 0.14% of the total the total spherical emission. What that means is if we were just to launch all the rays in a sphere around this uniformly, this cone is only 0.14%. Of that 0.14%, we're getting 72% actually to the detector. And that's actually pretty good. So I'm happy with that so far. And of course we can take a look at the spot size, which is going to be less good. We have this giant 5mm spot. And it's got this kind of smear to it. We really don't want that. We need to get the spot size down into the, hopefully tens, but potentially hundreds of microns so that it spreads over a few pixels. Ideally, when you're designing a spectrometer, you want to design your spot size based on your pixels so that it straddles, say, 1.5 or 2 pixels. If you match it to a pixel, you can sometimes get aliasing effects. All right, now that we've created our analyses, let's go ahead and build out our merit function. So we, as always, want soft efficiencies. We want spot size diameters. Now, let's think about our collection efficiency targets. Let's go ahead and just really quickly, let's calculate this merit function. So as you can see, we've got these very low collection efficiencies, and we're only really going to be able to get up to, a maximum we could do would be 0.41, or 0.14, sorry, which was the number that we got from our original collection efficiency run right over here. Right, we're only going to be able to get up to 0.14%. That's as much as we're getting into this cone. I'm going to make it a little higher just in case we end up moving things, but I would consider good enough to be somewhere around this value, which would be 0.12%. So now I've configured those two. As far as the spot size diameter, our target is clearly 0. I would be more than happy with 50 microns, especially for what we're doing right here. Going to save it. And then we have to consider what we are willing to optimize. Now, initially, we should probably just optimize the curvature of our two lenses. But we could eventually consider optimizing the rotation of the prism and the rotation of this coordinate system relative to the prism. But for now, I'm just going to start with the two radii, and then later we will add the others in as we get closer. So, radius of curvature, radius of curvature. Okay, and with that, we have created our merit function. So now let's go ahead and create our optimizer. This will be a sequential ray trace because we have a light path. And I'm going to tune up our max evaluations. And here we go. All right, now, moment of truth, let's run the optimizer. And we can see it pretty much immediately has dialed in our light. But we're immediately seeing a bit of a problem, which is that the red light is not focusing to anywhere near as small of a spot as the white light, or as the violet light. So this is where we're going to start to include the other optimization variables that I mentioned. So let's go back to our merit function, and we're going to include a couple of things. The first is going to be Y shift. Now, unlike the radii, we're going to bound this pretty tightly to prevent bad things from happening. That seems about right. I mean, we're already pretty close, so I think this is good bound. Then the other parameters that we're going to allow the optimizer to adjust are going to be a couple of angles. The first angle is going to be the rotation of the prism in degrees. So prism x rotation. And we're going to keep this pretty tight. We'll let it go down to 15 and maybe up to 25, maybe 23. And we'll see if it hits one of those bounds, we might widen them. But we don't want it to go crazy on us. And then the next one will be for focusing. So I'm going to edit that one and bring this up. And that's going to be the x rotation of focusing. So we're going to go to focusing, rotation, x. And again, we're going to keep this pretty tight. Maybe down to 20, maybe up to 30. And we're going to save it. Now we're going to rerun the optimizer. But before we do that, I'd like to get a baseline of how we're doing from our merit function. Let's go ahead and take a look. So the current value of the merit function is 33.31. And actually looking back at it one more time, far and away the worst offender is this very large 0.73 diameter for red. Our collection efficiencies for both red and violet are looking pretty good. They haven't changed that much because there wasn't really much gas in that tank. And then we've actually gotten the violet spot size down below our target. So it's really just the red. And that's what we hope we can at least reduce a little bit in this optimization. Okay, so now that we've analyzed that, Let's go ahead and run the optimizer. And away we go. We can see our merit function is dropping. We started at about 33, and we're going down a bit to 30.844, and I think we basically stopped right about there. So I'm going to go ahead and stop this. Now, as you can see, the spot size just from looking is going to be larger on the red, but let's take a look and see how we've done in the actual merit function itself. Let's go ahead and open that up. And you can see that we brought the spot size down considerably from in the mid-70s down to about 0.065. This has also decreased a little bit, and we've correspondingly been able to reduce our overall cost for our merit function from 33.31 down to 30.8426. Let's also take a look and see if we're running up against any of our limits. So we are running up against our Y-shift limit. It's trying to shift it more, and we're not letting it. We're also running up against our focusing limit. Let's go ahead and loosen both of these limits. I'm going to loosen shift to about 10, and I'm going to loosen focusing rotation up to 40. And now let's go ahead and run this again. And there we go. We were able to drop it a little bit more. Ooh, that, that doesn't look very good. We're starting to get some weird looking results here. And it looks like we could probably still keep going, but I'm going to stop it here for now because we're about to run off the edge of our detector. But let's take a look at the merit function again. I just recalculate it. So again, we've reduced it a little bit from 30.84 down to 29.96. These are roughly unchanged. This has gotten worse. This has gotten a little better. And that's more or less where we've landed. Now, let's also take a look here. Yes, we're now hitting the limit on our X rotation, on our focusing. So we haven't gotten the kind of satisfactory answer that we wanted, where both of these are focusing to small spots. Let's take a look and see what the optimizer is trying to do, because we can learn from this. Fundamentally, what the optimizer is trying to do is it's trying to make the path length that the red light takes longer than the path length that the violet light takes. It's essentially trying to correct by tilting for the chromatic aberration that is occurring due to this lens element right here. So this makes for a pretty obvious observation that if we were to replace this lens element with an achromat, we could probably avoid all of this skewing that's going on right now. And we could probably get both of these spot sizes to be much smaller. So let's go ahead and give that a shot right now. All right, so we're going to go ahead and make some edits here. We're going to change this to a BCX lens. And we're going to also create, and that of course has made everything invalid down here. We're going to go ahead and create a meniscus lens that will be on our focusing coordinate system. And we're going to rotate that 180 degrees. We're going to go with NF2, if I can type, to match our NBK7 and to form our achromat. And we're just going to go ahead and add it, even though we know it's not in the right position because it's just at the origin here. So now the next thing we're going to do is we're going to add spacing to form the achromat. This is going to be spacing between 2 and 3, and it's going to be 0. Now we notice that this is not exactly where we want because we still have to apply the Y-shift to actually form the achromat itself. So let's go ahead and put the Y-shift in. Okay, save that. All right, perfect. So now we have our achromat almost. We have one more thing to do. We need to add the common radius for this element. go ahead and create a formula, achromat R. And for free variables, R. And I don't know what the R currently is. 50, okay, well, we'll start with 50. Seems like a good place. And there we go. We're going to drag this up to the top, and we're going to make it so that the radius right is achromat R. And the radius right of this, because it's rotated 180 degrees, will also be achromat R. And here we go. So now we have our achromat. And now I'm going to do a couple of things. I'm going to fix the light path, make sure everything becomes valid again. And then I'm going to edit the merit function so that we can actually optimize this achromat. Let's go ahead and start with the light path. So the issue with the light path is that the surface references got broken when we changed its type. So I'm going to go ahead and it's going to be left, then right, and then we need to do the same thing for revolution body 2. Go ahead and actually add these. Sorry, revolution body 3, which would be this one. That's going to be right and then left. Okay, I'm going to drag these into the right spots. All right. Now with any luck, when we recast this light, it will actually make it through. No dice. So let's go back and see what we broke in our light path. Well, if we recall, revolution body 2 was originally a PCX lens, and we actually rotated it 180 degrees. So that actually means these segments need to be swapped. Okay, now that we swapped it, let's cast them all and verify that it works. All right, perfect. We can see that we're now focusing way ahead, but we can certainly still see the separation. All right, so now that we've set up the achromat and configured the light path, we're going to reset some of the tilt and other configurations that we did during the first series of optimizations. And I'm also going to remove those parameters from the merit function to simplify the optimization and make it more likely that we get to a good place before we allow the tilt and rotation to fine-tune it. So the first one was the rotation on Prism. We originally set that at about, what was it, 18 degrees. So I'm going to go ahead and turn it back to 18 degrees. And then focusing, I think our original rotation was 25. So I'm going to put that back there to 25. And then our original Y shift was only 2.5, so I'm going to put that there. And now I'm going to recast all of the light. Okay, good. So now we're a lot less shifted and skewed. We're back at our original starting positions. And I'm going to open up the merit function. Move this over here so we can see it. And I'm going to go ahead and remove Y shift and the rotations. So the only thing that we can now vary are the radii. So now I'm going to save that merit function, and I'm going to run the optimizer. Here we go. All right, oh, we can see we're not tightening up nicely. And our merit function is down at 10. We've never been anywhere near that low before. Let's go ahead and stop and take a look. Now what I'm seeing over here is a very bad looking achromat. Our lens is too thin, so we're going to need to allow it to be a bit thicker. I'm going to go ahead and increase its center thickness to 10. There we go. So now this will allow this central radius to vary a bit more. So let's go ahead and rerun the optimizer one last time, see if we can improve things still further. All right, there we go. You can see it's really dilated in now. We're down at a merit value of 5. And we're going to stop right now. Now let's take a look at the achromat that we've built out here. And it looks pretty reasonable. I'd obviously like this curvature to be a little less, but for our purposes that'll work. And now let's take a look at the merit function. As you can see here, we've actually gotten the spot sizes down considerably. Red is actually now smaller than violet. So we're at 59 and 32. We're almost within our goals for both of them. We did give up a little bit, going from about 10 to about 9.8 in terms of collection efficiency. But this is looking remarkably better than where we once were. So now we're going to allow for us to vary and shift, or to rotate and shift in the merit function. Let's go ahead and add a Y shift. And we're going to add prism rotation in the X, and we're going to add focusing rotation also in the, whoops, that was Z. Focusing rot X, there we go. Now let's scroll down, we're going to delete the one we put in. We're going to just bound this very tightly. Let it go up to 10. X degree, sure. That's fine too. Okay, great. So now let's move this over just a bit, and let's rerun the optimizer. You can see we're dropping pretty substantially. Now what this is doing is it's trying to correct for the chromatic aberration that's getting picked up in this first lens that we did not turn into an achromat. And so it's still going to try to tilt it a little bit. And it's still tilting. But we notice that it slowed down. We got most of the gain here. And if we were willing to accept this tilt in our design, this could be good enough. It is cheaper to tilt these things than to potentially turn this into an achromat as well. But let's take a look at our merit function and see how we ended up. Okay, we've actually gotten our spot sizes down very considerably to 13 and 10 microns, which is actually around pixel size for many common CCDs. And to do that, we did not have to pay very much in terms of collection efficiency. These started at about 0.0010, and they've essentially stayed there the whole time. Now we did lose a little collection efficiency because we put in this achromat, and given our wavelength range, we could get some of that back with anti-reflective coatings. But I'm happy with how we're doing right now, and I think that this is good enough. So now that we've succeeded in getting most of the light through our optical system and onto our detector, and we've also succeeded in getting very small spot sizes across the spectral range that we are interested in, let's go for the view that we've been waiting for. Let's take a look at the rainbow we have created. I'm going to go into Display. I'm going to uncheck red and violet, and I'm going to turn on our uniform emission. And of course, we didn't cast it, so that's a little anticlimactic, but let's go ahead and cast that. Whoop! There we go. Taste the rainbow. Here's our uniform light. It's traveling through our spectrometer, and it's getting split by wavelength at our detector. And if we just zoom in here, we can see that we've got this nice, narrow, well-focused beam of light that we could position right onto a detector and analyze. Now, one final note just before I wrap up. You would want to change probably the thickness of this lens and definitely the thicknesses of these lenses for better manufacturability. But this is more of a theoretical exercise anyways. So let's move on to the wrap-up and overall conclusions. We began this video with the observation that if we could put an element in between our point source collection lens, and that element shifted the light slightly based on the wavelength, that this lens element here would see slightly shifted but still collimated beams of light, and it would correspondingly focus them to sharp spots based on the wavelength. The prism has a varying index of refraction by wavelength, so it accomplishes this. It shifts the red light the least. It shifts the the violet light the most. The violet light gets pushed down at a sharper angle, travels through our achromat, and gets focused here at the bottom of our detector. The red light travels through with the least amount of refraction, and it gets focused at the top. All we've done is essentially created a point source collection lens with an element like this in the middle. And to reiterate, a Scherz-Turner spectrometer is exactly this approach, but with mirrors rather than lenses. And the big advantage of using mirrors is that mirrors do not have chromatic aberration, so you do not have to create achromats like this, or use specialized materials to create an achromat that would work over, say, the UV vis range. Well, all right, that is all for this video. Thank you very much for watching, and I'll see you next time.